Archiving started.
All right, can I have everybody's attention? I want to introduce our speaker today. This is Victor Shum. He, he's not just some random person we picked to be speaker. He actually has taken many physics classes here, so he can, after the talk, if you want to talk to him about some of the experiences of what it's like being a student here, he's a good person to talk to about that. And also, he's been involved in several different areas of research, I think from aerospace and computational physics and computing, and then now he's doing some stuff with breast cancer research. And so, like I said, there's a lot of, he's a good person to ask these questions to. So with that, I'm going to turn it over to Victor.
Thank you, David. So today, as David mentioned, I spent some time here taking courses in physics, especially in the, I took relativity, not relativity, but mathematical physics 1 with me, yeah. And then I move on to do some more research. I think this is the one research. I'm very fortunate that I met with Dr. Gabor Zalazi, who is the principal investigator for this research in MD Anderson Cancer Center. And his background is also in physics, University of St. Louis in physics, and he originally was doing more on stochastic research. But there is a postdoc biologist in the lab that is mainly doing breast cancer research. So I'm collaborating with Dr. Jingho Lee, who is has specialty in doing breast cancer research. So today I'm going to talk about the master regulators of 3 important genes in breast cancer. We call it those are transcription factors, meaning that they transcribe from DNA to mRNA, and then from mRNA, then we have the proteins associated with these genes. And the core of this, the core is the ER alpha, which is important for breast cancer in a lot of ways. In normal person, ER alpha has to do with growth as well as differentiation of the tissue. So I'm going to go through in the big picture regulation with transcription factor as the basis for. So all these transcription factors can be thought of as the CPU of the cell function. So the regulation is important. That's why we're going to study the transcription factors. And I'm going to go through some of the significance of these 3 genes in breast cancer, and I'm going to talk about how to model and parameterize the regulation between these two genes. The second part will be the estradiol effect on this network, and the third part will be the triad, which is all 3 genes together, preliminary results on the stability analysis. So everything goes down to the central dogma of molecular biology, which shows us that with the gene, with the DNA in the nucleus, we have a sequence of nucleotides, and some of those relate to codons that generate different proteins. And transcription factors, typically they group together into co-regulators as a machinery to start. This arrow means that it's the starting codon for the transcription process to start. And then once transcription starts, it will produce a reading from the nucleotide, the messenger RNA, which in turn will produce the protein, because the polymerase II is the reading head for the mRNA, which code for the proteins themselves. And the main thing is that these proteins can themselves come back and bind to some of the responsive sites. Typically, a few kilo bases in front of the transcription start codon, and some of which even for our case, the ER alpha can actually be responsive upstream up to 100 kilo bases. So we call them enhancer sites if it's further away, and we call them promoter sites when it is closer to the transcription start part of the DNA. So our main focus in breast cancer is that we have this core receptor we call the estrogen receptor alpha. There's also a beta version which is more related to prostate cancer. But the main thing is that the ER alpha itself is a large transcription factor, and it's regulating three main things. One is the growth. So in male and female humans, growth is in some ways related to this receptor transcription factor. Also that for epithelial and luminal breast cells, breast tissue, it controls the differentiation into these tissues. It also controls the cell cycle for proliferation of different cells, and apoptosis, which is regulation cannot go without apoptosis, which is programmed cell death. So regulation itself depends on transcription synthesis of these new proteins, and also apoptosis, which is the programmed death of that. So it goes into equilibrium by these generation and cell death processes. But also that estrogen receptor alpha is in turn regulated by important transcription factors beta-3 and FOXA1. And during tumorigenesis, the mammary glands have distinct ER alpha status that can be subdivided into ER alpha positive and ER alpha negative subgroups. And over 70% of primary breast cancers, primary means that it resides predominantly in the breast. It actually can go metastatically, and it likes to go to the lungs and bones. So the primary breast cancers is mostly 70% estrogen alpha positive, which means that we find expression of these levels high. And the overview, as we know, so the ER alpha is the core transcription factor in the center, and I've just talked about is a relation with differentiation, which is what we're focusing on today, the epithelial luminal. So luminal means the ductal part of the breast tissue, and it's regulated by beta-3, and it dimerizes by estrogen, the hormone estrogen molecule here, and it also controls cell cycle, apoptosis gene, and I think Rice University, Dr. Levine's group is interested in the EMT, which is the epithelial mesenchymal transition into the transition into more invasive types of breast cancer cells. So beta-3 What is GATA3? GATA3 is one member of a data transcription family with finger motifs, and these finger motifs helps to identify these DNA sites, the sequence in the DNA, but it also promotes chromatin remodeling. So it actually remodels some of these estrogen receptor responsive sites. So, yes.
What do you mean by remodeling?
Remodeling means because there are machinery that is responsible for, like for example, back to this picture here. So all these, I'm showing it as a linear DNA sequence here, but actually there are two-dimensional and three-dimensional sheets and 3D structures corresponding to DNA readouts. So remodeling means that it actually helps expose these naturally, these DNA are bound to histones in our chromosomes. So it has to be open up. So some of these nucleotides has to be opened up to be identified by these machineries here. The machinery being the polymerase II. Yeah, the polymerase II would be the machinery to read out these nucleotides. But these transcription factors, called regulators, we call them, are there to actually help opening up by different processes like acetylation, deacetylation. So we open up by deacetylation and demethylation. So these two important processes to help. So GATA3 also is implicated in very important way by there's a talk by Xenograft in the University of San Francisco, and it actually is responsive in the pathway of the transition pathway to more invasive types through the activation of the microRNA 29. So it's also important in that respect. So the basic action is what we're looking at is the binding affinities. The binding affinity of what I'm showing here of the chromatin immunoglobulin precipitation process, which identifies how the protein binds, the affinity of the protein binding to this DNA. So the higher this, the bar here means that it has higher affinity, and with the so along the different nucleotides of this gene, ESR1 gene corresponding to the ER alpha protein, there are different affinities at different distances. So these are the highest ones actually are further away, so we call them the enhancer sites. ENH stands for enhancer sites. And correspondingly, the GATA3 also, the GATA3 gene itself, before the transcription starts, they're upstream. This is upstream of the transcription starts. Nucleotide sequences is also have high affinity in the enhancer regions of the GATA3 gene. So, what do we want to find out? We want to find out the interaction between these two genes. So, the ER alpha, the ESR1 gene makes ER alpha protein, and it binds back to itself. It also binds to GATA3, which has the ER alpha protein site, and GATA also binds to ER alpha. So they are regulating each other. But how are they regulating each other? Is it directly positively regulated with an arrow like that? Or is it negatively regulated? Or is it not regulated at all due to some reason? So each of these branch has 3 different regulation possibility. So there are 4 of these branches. So 3 to the power 4 is 81 different ways it can regulate each other. So the way that we do our experiment is to knock down with interference siRNA to each of these genes. So we can add siRNA ER to knock down the ESR1 gene effect. We can also use the GATA3 siRNA to knock down the GATA3 gene. And we look for both the protein degradation process, which we want to, so we can get from the degradation after knockout as a rate of protein degradation in terms of half-life. And also, we can also look at after degradation, how is it recovering from the knockout process.
So these are all standard breast cancer cell lines in vitro?
Yes, these are standard ones, MCF7 and then T47D, which both are having positive expression of ER alpha, mostly. Yeah. So after doing this experiment, we use mathematical optimization schemes to search for network topologies and estimate model parameters. So these are the experiments I was talking about. So if we knock down ER alpha, we call it ER alpha siRNA knockdown. After doing that, we look at both of these protein levels. We also look at the mRNA levels, but here I'm showing the protein levels, which you can see from Western blot, which is the standard process to look at the darker it is, the more concentrated it is, the more highly expressed it is in the protein. So we look at the expression of these proteins through Western blot technique, and then we look at how they are degrading over time. So from these 2 plots, we can estimate the degradation of ER alpha protein and also the degradation of GATA3 protein. And then from the recovering graph, we can estimate how much they have recovered, the level of recovery from control. So control, it should recover to this level. The knockdown of GATA3, they only recover at this level. So we do ER alpha siRNA knockdown, look at the control, which means that without knockdown, what is the recovery without? Only the recovery itself is from the protein. So there are two parts to it, right? CHX here means that we don't just knock out with siRNA, we also remove the protein by the cyclohexamide. So the recovery is recovering from the removal of all proteins by cyclohexamide. So adding cyclohexamide, remove all the protein, and then remove all the protein. So both species, the ER alpha and gate 3 are both removed. And it will recover from, so the proteins will be regenerated by transcription again. Yes, that's the recovery. So the modeling, so we have the standard way to model it is by setting up different reactions, and the reaction types here are shown here. So the ESR1 is the estrogen receptor alpha gene itself, and either is not occupied by any of the ER alpha or beta 3 proteins, or is occupied just by M copies of the ER alpha protein, or it is occupied by N copies of the beta 3 protein, or is occupied by N copies of beta 3, M copies of ER alpha. And once it is occupied, the machinery, polymerase II machinery will be combined together to start the process of messenger RNA generation. And this messenger mRNA themselves are degraded naturally. The protein also is degraded naturally. So both the messenger RNA and the estrogen receptor alpha protein both are degrading naturally, through partly by ubiquitination. So the basic, we want them simple. So so for two species, if we try to model the transcription and translation process, there are 4 equations because each species has mRNA and protein. But to keep things simple, the mRNA, 2 of the mRNA equations, because they are the mRNA degrades fast, we can set the mRNA differential equation to 0 and make it steady state, and then put it back into these protein equations. And so what remains are only 2 equations involving these 2 proteins. Actually, it also includes the mRNA level, which by the algebraic manipulation, because it's protein generation is proportional to mRNA generation, we can produce only 2 of these equations here. And the sigmoidal function here is used to capture the responsiveness. So each of these sigmoidal function, you can think of it as corresponding to like the recovery curve. Like the recovery curve, so the sigmoidal k determines how slow or how fast. So the k actually determines the half equilibrium point here. So if the k moves further, is higher k, the regulation would be more sigmoidal. If you have smaller k, the half equilibrium point will be moved closer, so that it will be it will recover faster, right? And also the power of the Hill sigmoidal function determines the steepness of the steepness, which means this faster response here is very steep here on this, the recovery, and these are slower ones. These are the slowest slope for these ones. So these have so it's less steep. So less steep means that this is a higher power. We call it the Hill coefficient than these ones. Yes.
Is that gel electrophoresis that you're using up there?
Oh yes, this is the after gel electrophoresis, then we can actually expose it to imaging, and then we can use the software ImageJ to look at the intensity and correlate it with the expression level. Yes. It's the other way around, sorry. Okay, so these are two basic equations we use to generate different types, and this is it's normalizing it to remove two parameters. So this has more parameters, like the rate of degradation here. You can see the negative sign here. This is the GE, is the rate of alpha degradation, and GG is the degradation rate of beta 3. And then we can normalize it by dividing these over, and we have this normalized equation, which the maximum of the expression will become 1 with this normalization. So also that because of this normalization, we can set the different flow change here. The flow change, which the V1, V2, V3, V4 corresponds to the strength of this branch. The higher the number it is, the higher the strength of the branch affecting the other one. So we can use this to set the V1, V2. So these 4 numbers are very important numbers to show the sign, if it's repressive or if it's activating. So just by looking at the V1, V2, V3, V4, if it's less than 1, it will be repressive. From 0 to 1, it's repressive. If it's completely 1, it will actually cancel the normalizing factor, and so it will not affect anything. If it's bigger than 1, it is activating. So by looking at these, if it's from 0 to 1, 1 or bigger than 1, we can see if it's activating, repressing, or it has no effect at all. And another normalization is by normalizing with the equilibrium. We call it the E0 and E0, G0 here for equilibrium level here. So there are 3 strategies. Actually, we try to be sure that the parameters are good. So I first started with the taking all the 81 different possibilities and rewriting by computer all the different equations, repression and activation and null. And then there is another way to do it, is what I just talked about, is by looking at the V1, V2 ranges. And the third one is just using the 2 equations and put in all the random starting numbers for the parameters, because they are real numbers. They will actually go across all the different space. So there are 3 ways, and we went through all 3 ways to make sure we are correct. So the first way is that we rewrite each of these equations into, if its ER is repressing beta 3, its form will be the K factor on top.
Is that the V3 and V4 at the bottom?
Yes, yes. Yeah, there's a typo here. Thank you. So V3 and V4 at the bottom here. Thank you. So yes, that's a good catch. So activation is by putting the protein level on top. Repression is putting the K factor on top. So there are 81 of these set of equations that I used to do this. And the other way is to look at the V. So with different these, we can do optimization for each of these time courses, for knockdowns, and for knockdowns here, and for so mainly for looking at knockdowns, we can separate out the self-repression of E from the first row. From the first row is the G repressing E. The second row is nothing. The third row is activation of E. So just by looking at the match, and we see that the bottom one has the highest match. So the fitness function actually is the best one for the data activating E. And also for the other one, the top one is the most the best match. So it corresponds to the E repressing G. So we can use that to look at the different paths.
Can you tell anything from the slope?
From the slope.
Like the inhibition of data looks
Which one?
less than this. The top left, the top right looks a little bit less effective than the bottom left. Is that true? Can we see that? The inhibition of data.
Which one is it? The row, the first. You're talking about this
Top right.
top right. This one.
Okay. The slope looks like it's not as effective as the bottom left. Is that true?
This bottom left.
No, it's bottom left on this one. Data is enhancing the E expression, right?
Oh, the bottom left here. Yeah. Okay. You're saying this is looks more effective than this one?
That looks a little bit more effective than the top.
Yeah, we can actually use that information. Yeah, which would give us a higher strength of this one here.
Okay.
Yeah, you're correct. So this has a higher strength here. So there are two different phases. One phase is looking at the steady state level and doing, like if we're using SI-ER to knock down, so we know the ER level already. So we look at the opposite data afterwards, and we look at the objective function. So this is for steady state where we already know the knockdown level of one species and look at the other species. And we also look into the response time. Here on the right is response time. So according to lots of research, the positive regulation actually favors a more sigmoidal type of recovery, and negative regulation corresponds to a faster response, so that actually would be less sigmoidal and more linear on the first. So this part before it saturates, it actually is more linear with negative feedback. So we can actually look at the recovery curve and see if it's positive or negative feedback. So with steady state, so we can do the separation from, these are our system numbers, 81 of them, and it can separate out the system from the one, the minimum of that would be the best system fit. And then we can see that we can have the best fit with two of these systems, which is one is positive, one is no regulation. And then we have to do some more because these two systems are not too far away. So we do have to use to look at the self-regulation. So if it's going to be null or positive or negative here, we use a specific drug for ICI, which can target ER alpha directly itself. So we can see the self-response of ER alpha. This is the self-response of ER alpha by using ICI. We can see if it's negatively responsive or no or positive, right? So ICI is like tamoxifen. It degrades. Basically, it's a drug that degrades ER alpha protein in the cytoplasm. It's removing the protein in the cytoplasm. Yeah. So it's specific to the ER alpha protein itself, so that we know that it would have an effect on the cell regulation of ER alpha. So if it's a positive regulating, then it should go down. Negative should go up. If there's no regulation, it should stay flat. So in the relative mRNA experiment, we actually see that with very high dose of ICI, it is pretty much flat with a little bit upward here, which is not statistically significant. So we can say that it suggests null regulation. So after all that's said and done, we can match all these different recovery and knockdown curves to have this kind of topology and the different strengths. And so, but there are errors. There are errors in experiments, and there are errors in the computation process. So how to range for error margins? So to range for error margins, we're not just looking at the best fit here. We are looking at the somewhat good fit. So when it's minimum flat here, we can select all those systems that is below a threshold that is pretty well matched, and look at them to see how much error that is in the computation as well. So we can also plot these curves and to see the spread of the errors. So we can see the spread of the errors is highest for the data tree here. But there are errors. And also because of the, there's a risk of undersampling. So the population, so how many iterations we go through this for converging optimization, we want it to be as many as possible, but for time's sake, we may not be able to do 1 million iterations. Each of these optimization will take over 100,000 iterations, and it will be months before it can go to 1 million. We're still going through the process of doing these iterations, but at the same time, we can also use the bootstrapping technique, which actually do resampling. And so I can use the top 2,000 and do resample for 1 million or 200,000 here, and look at the spread here, how much spread that is for each of these parameters here. We are looking at V1, V2, V3, V4, which is for the self, cross E to G, and then the G cells here. So we can actually determine how much spread that is in the computation. So these are the results for the optimization. So the powers of n here corresponds to the sensitivity, which I just mentioned, the Hill function sensitivity here. And the K determines it is more positive or negative regulated. The F, the strength of the branches. So that ends the first part, which is the regulation of ER and data. The second part is to study the effect of E2, which is estrogen, on this system. So the ER alpha has 4 different pathways. It's very complicated receptor. It can actually be ligand, which means that ligand means our estrogen here is a molecule, the hormone itself. The ligand independent one, you can see here ligand-independent pathway which responds to phosphorylation of the protein. The second one is the ligand-dependent, which is responsive to estradiol excitation. So the third one, the classical one is what we're looking at here. So E2 is our estradiol hormone here, goes into the cytoplasm of the cell, and it goes into the nucleus of the cell. Where
So the outer blue line is the cell membrane.
Right, the outer blue line.
The blue line is the nuclear membrane.
Exactly. So the cytoplasm is outside here, and the nucleus is in here, where all the DNAs reside. And with ligand means that E2 here, these estrogen are bound to these receptors here, R, and they form dimers. Once they form dimers, it will do transcription a little better. So this is the classical way looking at this hormone induced inside the nucleus. So for one thing, beta alpha can have oscillation. And this is from a Gannon paper that shows that the ER alpha, which is the black curve here, is oscillating ER alpha. And the main goal of this clock here is to, the first pulse here is to facilitate opening up histones, and the second pulse is for facilitating transcription. So it does need two pulses to set up the whole transcription process. And for our experiment, we try to stimulate our network by means of the estrogen stimulation. So we can have one-step pulse with estrogen, or we can have a pulse, a 1 hour pulse. We can start the lab sample by means of serum deprivation, and then we can add estrogen, and then we can remove estrogen quickly in terms of minutes. And we see that this is the response here. Well, we know that E2 actually form dimers with the receptor. After forming dimers with the receptor, it is preferentially degraded. Here is E2, ER alpha here. The protein itself is preferentially degraded here. That is with the step. And then it goes to almost a steady state here. That's the equilibrium level. ER, for beta 3, it's almost not touched. But for this, the pulse response, we can see that the beta 3 has a sort of oscillation effect here, and ER still goes down and go up a little bit, and a little bit of ripple there, but mostly on the beta 3.
Would the continuous estrogen stimulus be more realistic in vivo?
What do you mean by continuous?
The E2 stimulus being constant, right?
Yeah, this is the step. So we.
That's more realistic in vivo, like in the body.
Depends on the stages. Like E2 does fluctuate. Yeah, it does fluctuate.
But it doesn't pulse like that.
It doesn't pulse so fast in general. Yeah, it doesn't pulse like that. This is a little bit artificial here, just to stimulate the system and see what happens.
What exactly is the pulse? No, like what?
No, actually, application is just application of the hormone. So we apply estrogen and then remove quickly the estrogen itself. So it's application and removal. And before that, it's serum starting, all these using solutions to starve it of estrogen. So because of these stability, so we're looking at stability in this network. So we use eigenvalue classification. So if we can somehow linearize the system by means of equilibrium, how much movement above the equilibrium point. Equilibrium point being the equilibrium level of ER alpha, equilibrium level of beta 3, and as they move around, so we use the Taylor expression for the linear. So we can classify the eigenvalues from just looking at the partial of. So we can construct a Jacobian like that, which is looking at the partial response due to ER alpha, E here, or due to beta 3 here. So the partial of E, the partial of G on this first right-hand side, and the partial of E, the partial of G on this second right-hand side, would give us the movement. So this is the movement about the equilibrium point. How much movement? If the delta is large, it have more movement corresponding to each of these. So lo and behold, actually, our system is similar to a predator-prey system. We can use a whole lot of literature corresponding to this system. You can think about data as a prey, which has a birth rate. It self-activates, which is like a birth rate here. And ER alpha is like a predator eating up rabbits, like foxes eating up rabbits. And then E would be like a predator foxes supplied by the birth of the rabbits. And with this kind of system, we can do some normalization. Again, this sigma corresponds to what we had before. This is the sigma equals the amplification in the transcription divided by the degradation factor B and divided by the half equilibrium point. So this is a normalized factor here. And then we can plot it against the branch. This FA is activation, is also applied for repression. This is the branch strength. This corresponds to V1, V2 that are in my equation. So as we sweep across this, we can see that there are some regions where there's no oscillation, there's some regions with damped oscillation, and there are some regions with oscillatory effect. And so in our system, actually this is replicating first this system, we can classify these stability according to the eigenvalues, which is taking the determinant of the Jacobian, supplying it with equilibrium points, calculate the value, and classifying the eigenvalues. So the red one here corresponds to stable points. So it's always in equilibrium. It doesn't oscillate. It doesn't never be unstable, because both of these eigenvalues have negative real parts and no imaginary parts. So these are completely stable ones in these regions. So the blue ones will be the non-zero imaginary, which corresponds to more like the limit cycle one, where you have more persistent oscillation with equal amplitudes. Green one will be, the green one is actually corresponding to that limit cycle one. The blue ones are mixed unstable points. So as you plot the time plot, you can see that for these stable regions, both the ER and data can go down here. This is ER going up, data going. So there's stable, basically it's going through equilibrium directly without anything, no oscillation at all. And you can see damped oscillation in the other regions, in the blue and green regions. So fast forward to our system here, we can also see some damped oscillation in the region where the real positive. So we have two eigenvalues. One can be positive, one can be negative. if the positive is bigger, it's more dominant, so that it will oscillate a little bit. It's not both positive, so it's not as big. You don't see as big oscillation here.
Is this with the transient introduction of the estrogen, or is that?
Yeah, this is varying the parameters with these transient effect. Not directly. I'm still simulating the transient effect, but this is looking at the effect of estrogen as it knocks down the because it will have a higher degradation. It will.
Impulse introduction.
Yeah.
Okay.
Yeah. Yeah. This one is just by varying the parameters. The dynamic one I'm still simulating, so quantitatively I'm still running through the analysis. This is more like a static, rough estimation of where in the map it is, where if I vary the strength of these cross strength and cell strength and look at the transcription amplification, where in this location can I find this? So it will help my transient simulation. So we can also do some more to see that it could happen with different initial points and go to a resonant condition. This is with a delay on the transcription. So there may be a delay involved, but we can actually build resonance upon this system. So is there why do proteins oscillate? So what we find out before over the years is that there could be a rhythm synchronization with the 24-hour system as we evolve. There is also a system with the cell cycle in the yeast and human fibroblast. So we see this mouse liver, some of the cell tissues there respond to a 24-hour rhythm, the cell cycle within the 2-hour rhythm. There's some metabolic cycle rhythm, and these are unstimulated ones. And with the growth and MS covered B ones, the repair system oscillation, these can be stimulated into oscillation. So there are definitely some biological systems that can do that. And so it can actually, I think, more important once the cell cycle for proliferation process. So with that, I conclude the second part of my talk. The third part is the master regulation gene triad, which includes FOXA1. So what is FOXA1? So FOXA1 is a key factor in the redistribution of binding sites. So the chromatin of the R-alpha, which includes all the proteins involved in the DNA machinery, and it also found in case of patients having metastatic status resistant to drugs. So it's an important factor here.
These are binding sites on the cell membrane or in the nuclear membrane?
These are nuclear binding sites in the nucleus. Yeah, these are nuclear. We're studying mostly the nuclear binding. So that form a triad with the three fractures here, and the one interesting thing we can use it for is that there are breast cancer patients with metastatic, means that it can go from a primary tumor to a secondary tumor in the bone or lung. And if we can introduce, because ER-alpha positive patients, we can control with raloxifene or tamoxifen. We can have anti-estrogen drugs to compete with estrogen to actually cure some of our patients. So why not introduce ER-alpha into those with low levels of ER-alpha and program the cells not to proliferate, right? So people want to try that. But if we just do that with the one receptor, it doesn't work. it inhibits cell growth, so the cancer cell doesn't proliferate. So with the triad, we can actually introduce the whole 3 of these genes together and receptors, transcription factors, and affect estrogen responsive growth. So we recover the estrogen responsive growth by using all 3 factors together. So all of these factors, why are they regulating each other? Because they have binding sites for each other. Right? ER alpha has its own. Beta-3 has, ER alpha has 16 beta-3 binding sites. There are non-overlapping and overlapping binding sites. Together, they can allow binding from each other to regulate each other. So again, from Western blots and also from the mRNA relative, we can roughly see these regulation. So these are the ones we researched before, these 2 of these. And then the third one, we find that to be ER alpha is repressing FOXA1, beta-3 repressing FOXA1, and the only way FOXA1 recovers, because both are, the other 2 transcription factors are repressing it, is to self-generate, right? So we have a strong self-generating loop here. And to make sure we're correct, we also look at the mRNA level so that we see that ER negative regulates beta-3 from also mRNA. Also this, the flatness here corresponds to no self-regulation of ER. So the size of the problem is from these 2 equations, we have these 3 equations, including the FOXA1 and also the degradation, synthesis from transcription, and this degradation of the protein. And there are so many combinations. And to scale the problem, we can size down the, like in ER case, we can set the coefficient into different range. So with these different ranges, we can quickly eliminate reject many topologies together in one piece. So with one non-matching F, the cross strength and the cell strength, we can eliminate a whole bunch of topologies. In the 3-dimensional one, we can, each of these can eliminate 54 cases. And we also use the Exceed system, which is Pittsburgh, because why I'm choosing Pittsburgh? Because they have MATLAB licenses there. So that's a constraint. So I'm actually moving away from MATLAB itself because there are some license constraint. I cannot use all of these nodes altogether. So that's a big constraint, but it helps to improve it. Execution can be faster by 42 times with 4 blades. And this is the interface I was using to run this. If you're using parallel MATLAB itself, it's PCT, which is scheduled to run your processors. How many cores in your processor can run is PCT, but on the blacklight there will be another level of parallelism, so we can use the different nodes to run things in parallel. So another way to quickly get a hold of the system, how it is corresponding to the strength respect to the transcription rate, I try to look at the signature of this stability map by changing the self-regulation of FOXA1, which is our system here, and with repression and with no, actually have all stable system, all stable to 0 because it's not sustaining itself, and both are. So it's pretty obvious. There is other validation that this stability map is true. So in summary, 3 sections. We have concluded the topology of E and data into this topology, and we parameterize it with the hue function sensitivity, with the K half equilibrium point for positive negative regulation. And also, we look into the stability due to damped oscillation with excited by estrogen. And we also look into the triad stability map, which we're going to follow through with more quantitative results from time courses. So future prospects is, as I showed you in my first slide, there are different, so all the labs are migrating into full genome analysis because of the better computer system we have. So we're looking at all the genes in the genome, in our chromosomes, and just looking at the master regulators is not enough. So we have to put our motif, the network motif, into the EMC motif, which is being investigated in another team in Levine's group in Rice University. And the cell cycle has its own circuit, so together we will piece together the whole network. And hopefully we can also build utility codes that can speed up optimization. Optimization takes a long time. The optimization stream I'm using is the particle swarm optimization together with interior points. So it takes from 10,000 to 1 million times to converge in one sitting. So I have to run it many times with random initial start. So if we can code and utilize all the clusters with a better one without license constraints like scientific Python or R, which many people are using in the statistics community, that would be another way to go. And the end goal is to produce multi-targeting medication for personalized medicine. So each person has his own circuit in terms of these genes. I can close my talk. And
okay. Questions? Wow.
So you're moving away from MATLAB.
Yeah, it has some license constraints. So, yeah.
Yeah, could you use something like Octave or
Yeah, Octave is one option.
From a bioscience standpoint, if you can look at other hormone interactions, I mean.
Yeah, ER beta.
Yeah. It's very sensitive to a lot of hormones, right? Insulin and testosterone and estrogen. There's a whole bunch of sensitivity there.
Right. It actually responds to a lot of things, and it targets a lot of genes. Like GATA3 targets 1,000 different genes. Yeah. ER alpha targets also another 1,000 genes. So another way is also we have a nuclear receptor a center in the University of Houston, headed by Gustafson, and he's he actually made the other form of this family called ER beta, which is mainly associated with prostate cancer. So researching ER alpha and ER beta together in one piece is another way to go.
Not just breast cancer, but all hormone-related cancer.
Hormone-related, endocrinic-related. There will be other kinds of, yeah. So also the P53 repair genes, which is a very enhanced digital nature. We know that the P53 and NDM2 regulates in a very digital nature after being radiated by ultraviolet light. The way it repairs genes, DNAs, are by pulses, and the pulses doesn't directly relate to the amplitude. It relates by the number of pulses. It has different number of pulses.
From ultraviolet light?
Ultraviolet light damages the DNA, and P53 is doing the DNA repair, so it's splicing back the DNA.
Why do you look at ultraviolet?
So this is the repair mechanism. So what I'm doing here is all hormonal pathways.
Yeah.
Yeah. So how is it related to the repair pathway? It's another network over there. So it's different from completely different hormonal pathways. So I'm looking at the bigger picture of the repair process. Yeah. Yeah, but the near goal is to mainly get down to the mechanism. Actually, ER alpha transcription mechanism is a very complicated process. So this is the logical next step.
Other questions? For this type of cancer, for the let's do phosphate 1 gave 3 ER alpha interaction, dynamic interaction between these compounds. Is the goal to kind of modulate the production of different hormones inside of the cell's machinery, like at the nucleus from the DNA?
Yes, that's the primary goal. The primary goal is so we regulate, as I say, so many different but the main three things is the proliferation versus growth and proliferation, the differentiation, and the cell cycle. So if we can control basically the cancer cell from proliferating, so that's the main reason. We can reprogram it by multiple targeting. So what's done today is we use tamoxifen or raloxifene, which are two anti-estrogen drugs that compete with estrogen, the hormone, to basically knock down the level of estrogen receptor only. So it's targeting one transcription factor here also.
So those essentially act as estrogen to bind to the sites that estrogen cannot bind to the site. Is that what you're saying? Like when it competes with estrogen?
Yeah, it actually dimerizes. It's the process of dimerization. When the hormone estrogen comes in, it helps the alpha transcription factor to form a dimer, a two transcription factor complex. And the dimer itself has the structure to bind better with the genes themselves, with the sequences. So the binding actually looks at the different sequences. That is proximate, so it can have affinity to that. So it's increased affinity of binding, basically.
Yeah.
So looking at it, the regulation means that we can both, we call it longitudinally. So what time should you apply these targeting drugs, and also what's the strength? So and are we targeting each one simultaneously? Right. So it's not just looking at just one receptor alpha gene and protein, but we are together looking at more and more transcription factors. And these transcription factors has many ways to disrupt regulation. It can help other co-regulators bind. It can open up the chromatin structure. It can relocate the chromatin site, binding site. It can have many different effects. So to target particular effects with no off-target effects, that's also another thing. So many of these, if you target a certain protein transcription factor, you have a lot of different unintended effects. So for example, this, if we use tamoxifen on breast cancer, ovarian cancer is more risky. It's ovarian cancer likes, so targeting one, you affect the other. So if you use tamoxifen on breast cancer, you affect ovarian cancer to have a higher risk. So a lot of drug companies are manipulating the chemistry of tamoxifen, and relaxafen is one evolved medication to target better breast cancer instead of having a risk factor on ovarian cancer. So the word here is personalized medicine. We know that we're building, MD Anderson Cancer Center is building a new building that is completely targeted for personalized medication. So you're targeting, each person has a different regulation circuit involved.
Based on their natural body chemistry, you just kind of modify the treatment. Right,
based on abundance, transcription factor delays, and different. ERF itself, the transcription itself is also highly related to degradation. The ubiquitination of these transcription factors can form a structure that helps transcription. So even for degradation, it has a clock there. We call it ubiquitin clock. O'Malley's group in Baylor. They are highly involved with looking at how ubiquitination, just the degradation of the transcription factor, will affect the transcription itself. So there is a complicated feedback regulation going on.
Okay. All right, let's thank our speaker. And I just have a few announcements. First off, next week is spring break.